Hi everyone, I'm Cesar from KTH Royal Institute of Technology in Sweden, and today I'm going to introduce you to our paper, A Longitudinal Analysis of Bloated Java Dependencies. We want to thank the reviewer and the PC Chairs for choosing this work for an ACM Distinguished Paper Award. The term software bloat refers to code that is packaged in an application, but it is not necessary for building and running it. Empirical evidence shows that software is bloated, from single unit commands to web browsers and operating systems. Most applications embed a part of code that is unnecessary for their correct operation. Software bloat is a problem because it needlessly wastes developers' time and resources. For example, software bloat increases the size of software artifacts, creates maintenance issues, affects performance, and compromises security. In the last years, research on software bloat has increased. However, previous work have not analyzed the evolution of bloat over time. In this context, understanding software bloat from the perspective of software evolution is crucial to promote debloating tools to software developers. In particular, when proposed to use a debloating tool, developers wonder if a piece of bloated code might be needed in the coming releases of the project. Our paper constitutes the first longitudinal analysis of software bloat. In particular, we are focused on the evolution of bloated dependencies in the Java Maven ecosystem. Let me show you an example of the evolution of a bloated dependency for an hypothetical project P. We are going to visualize the dependency tree in different versions of this project. In particular, we are interested in the usage status of its dependencies. In the beginning, version 1 of project P has no dependencies. Then, when releasing version 2, developers decide to reuse some functionalities from third-party dependencies, A and B. To do so, developers just need to edit a particular file called the POM file in the Maven projects. This way, A and B become direct dependencies of project P. Then, the third version of the project is released. At this point, the developers of dependency A decide to augment its functionality and declare two more dependencies, C and D. These are now transitive dependencies of project P. Suppose that developers of P don't use the functionality of B anymore. Then, this dependency is not used and becomes a bloated dependency of project P. However, although unnecessary, developers keep this dependency in the POM of P. For example, because they are not sure if the dependency will be necessary in the future. In the subsequent version 4 of project P, dependency B remains bloated, but now the transitive dependency D is also bloated. As we can observe, the usage status of dependencies in the dependency tree of a project may change over time. Our paper focuses on studying this phenomenon using empirical data. We articulate our work around 4 research questions. Our first research question focuses on analyzing the evolution of the number of bloated dependencies. Next, we investigate how the usage status of dependencies evolve across time. This analysis is a key contribution of our work where we determine if a dependency that is bloated is likely to remain bloated over subsequent versions of the project. Our third research question focuses on the unnecessary maintenance effort induced by bloated dependencies. In particular, we investigate how often developers modify the POM files to update dependencies that are actually bloated. In the last research question, we expand the quantitative analysis of the status of each dependency and perform an in-depth analysis of the causes of dependency bloat. Due to the time constraints for this presentation, we are going to discuss the second and third research questions. If you are interested in the rest as well as in the details of our analysis, you are more than welcome to read our paper. The dataset used in our study consists of a collection of subsequent versions of Maven dependency trees. Our data collection pipeline starts from the list of Java projects extracted from GitHub. In the first step, we identify the Maven single module projects on GitHub. We then select 500 projects that have the most number of releases. In the second step, we check all the commits made on the POM file. Each time the version of a project changes, we consider that the commit represents a new release. In the third step, we analyze the status of dependencies in the project at each commit. We label each dependency as used or bloated. Our final dataset consists of 31,515 dependency trees. To answer our second research question, we investigate how the usage status of dependency changes over time. The figure shows in the y-axis the sequence of usage statuses of 4 dependencies in our dataset: Apache Common Langs, H2, HTTP Mine, JSON, and Guava. The y-axis represents the date when the dependency was analyzed. Green dots mean that the dependency was used. Red diamonds mean that the dependency was bloated. We determine 5 transitional patterns: U, when the dependency was always used; B, when the dependency was always bloated; UB, when the dependency was used and then bloated; BU, when the dependency was bloated and then used; and fluctuating, in the case when the usage status of a dependency flickers over time. We compute the percentage of occurrence of each pattern with respect to the total. We found that 64.3% of the direct dependencies are always used in the project, whereas 29.9% of them are always bloated. This means that most direct dependencies never change their status through the evolution of the software project. On the other hand, 78.3% of the transitive dependencies are bloated from the start, whereas 12.8% are always used. This means that transitive dependencies also do not change their status over time. 89.2% of bloated dependencies and 93.3% of the transitive bloated dependencies remain bloated in all the subsequent versions of the studied projects. This empirical evidence suggests that developers can safely take a debloating action when detecting bloated dependencies. To answer our third research question, we investigate whether or not developers maintain dependencies that are bloated. We filter all the commits in our dataset that constitute dependencies updates. The figure shows an example of one of such commits. In this case, a developer manually updates the dependency of Apache Common I/O from version 2.6 to version 2.7. During our analysis, we noticed that many of the dependency updates were performed by Dependabot. This is a software bot very active on GitHub that alerts developers about security issues related to their dependencies. This plot represents the number of direct dependency usage, unused and bloated dependencies made by developers. As we can see, developers invest 22% of their dependency updates effort on bloated dependencies. On the other hand, we observe that Dependabot suggests a similar ratio of updates on bloated dependencies. This result indicates that Dependabot should improve the suggestion that it made to developers to detect bloated dependencies and reduce the maintenance effort induced by software bloat. So, 22% of dependency updates performed by developers and bots are made on bloated dependencies. This is evidence that software bloat artificially increases the maintenance effort of software projects. This effort can be minimized by removing bloated dependencies, which is safe because, as we've found in the previous research question, bloated dependencies are very likely to remain bloated in the future. We invite you to read our paper for more details on this work, and feel free to contact us if you have any questions or comments. Thank you very much for watching.